Can we start, Dubey sir?
Yeah, okay, fine.
Yes, sir. We are honored to have you with us today, sir. Dear participants, just a brief introduction about Shivram Dubey sir. Shivram Dubey sir has been with the Indian Institute of Information Technology, IIIT, Series City since 2016, where he is currently the Assistant Professor of Computer Science and Engineering. He received the PhD degree in Computer Vision and Image Processing from Indian Institute of Information Technology, Allahabad in 2016. Before that, from August 2012 to Feb 2013, he was a project officer in the Computer Science and Engineering Department at Indian Institute of Technology, Madras. He was the recipient of several awards, including the Indo-Taiwan Joint Research Grant from DST Government of India, Best PhD Award in PhD Symposium, IEEE CICT 2017 at Gwalior. Earlier career research award from SERP Government of India and NVIDIA GPU Grant Award twice from NVIDIA. He received the Outstanding Certificate of Reviewing Awards from the Information Fusion elsewhere in 2018. He also received the Best Paper Award in IEEE UpCon 2015 and prestigious conference of IEEE UP section. His research interest includes computer vision, image processing, deep learning, biometrics, medical imaging, convolutional neural network, generative adversarial networks, and CNN coding, etc. Thank you, sir. We are honored to have you with us today, sir. We are eagerly waiting for your talk. Over to you, Dubey sir.
Thank you very much, Dr. Rupa, for this nice introduction. So first of all, welcome to all of the participants, whoever is presenting this particular session. So majorly, I am going to talk about this generative adversarial network, basically, which is one of the recent, let's say, developments that has happened in artificial intelligence area, and majorly applied to computer vision problems. And I also hope that because this is going to be fourth day of this FDP program, then by this time you would have already let's say learned a lot of things which is basically related to convolutional neural network or deep learning, or let's say how to train deep learning, and what are the basically nuances in deep learning in terms of what could be let's say best practices when you are going to use this convolutional neural network for different applications. Applications may range from image classification to object recognition, image segmentation, or even you can have the applications even beyond computer vision also. For example, even it can be some time series, let's say data classification, or some ECG data classification, EMG data classification. So if you see, there are plenty of applications basically which is basically currently nowadays being dealt with these deep learning based models. And out of those deep learning based models, these convolutional neural networks based models have gained let's say a huge popularity. And the first convolutional neural network model that came basically in picture, or that came in let's say highlight basically in 2012, that was AlexNet, and that basically owned one of the very challenging image visual recognition challenge, that is called basically this image classification challenge. And that is generally basically organized by Stanford University along with other let's say collaborative universities. And after that, a lot of development happened, and a lot of let's say several CNN models came basically for different applications. For example, AlexNet was winner in 2012. Similarly, in 2013 there was a winner for this particular challenge, which is called ZFNet. In 2014 the winner was basically this Google Net that came from the industry, this Google architecture. At the same time, there was one more model which became very popular, that is called VCC, which came basically from Oxford University. And after that, there was a model like residual network, and then one of the recent model is called the squeeze and excitation network. So there are different such let's say CNN models basically that even they actually surpass the human level performance. Even for different applications also, for example, object detection, there are models like fast RCNN, faster RCNN. Nowadays there are models like YOLO and SSD and even RetinaNet. Even there is recent developments that is happening in object detection to go in more real time, as well as to also to improve the performance of the models. Similarly, what happened while this all this progress was happening, in 2014 there is the first work that came in generative adversarial network, and that actually came from Ian Goodfellow. So if you see this, basically what is this generative adversarial network? So generative adversarial network is basically trying to generate new samples, let's say in a given set of samples that we have in the same distribution that we have. So suppose if you have a data set and if you want to generate more images that should be like the images that you have in your original data set, then basically this generative adversarial network is going to be useful. Or even suppose if you want to transform one image, if you want to transform an image from a domain to any other domain, then also this generative adversarial network is going to be useful. And basically that problem generally referred as image to image translation problem. So what we are going to do in today's session, basically in this session we are going to start our discussion with let's say a very fundamental let's say aspect of the whole machine learning area, that is called supervised learning and unsupervised learning. I hope that all of you are well aware with such kind of things, but we will just take 5 to 10 minutes to start with that, because generative adversarial network is one basically type of a network which generally relies on unsupervised mode of training. So we will just have a quick look over that, what are the differences between supervised and unsupervised type of let's say these models, and then we will continue our discussion. We will take one example. We will take a small discussion of autoencoder just to develop the basically background for generative adversarial network, and then we will continue our discussion to generative adversarial network, the concept, and as well as what are the developments that has happened recently and how this generative adversarial network is basically nowadays being used in image to image translation, and what are the let's say popular models in this image to image translation using generative adversarial network, and what are the general applications generally where nowadays people are exploring the use of this generative adversarial network in different scenarios. So I'm just going to share my screen here, and I have one presentation that I have prepared. So I just want to start with this presentation. Just a quick, this is just a sanity check that I'm properly audible, as well as my screen is shared and it is visible to you. So then after I will just start.
Yes, sir. We are audible as well as the screen is displayed, sir.
Okay. Thank you very much. So now, before let's say going to actual generative adversarial network, a quick look over this unsupervised learning, and then what is autoencoder, and then we will go to the GAN, and then what are the recent trends in the GAN and its applications. So if you see broadly, basically all learning techniques are classified into supervised versus unsupervised. We have some different modes also. For example, we have semi-supervised, self-supervised. So excluding those other supervision methods, broadly things are categorized here into two parts, supervised and unsupervised. If you see supervised is very simple. So supervised means that along with data, we also have that what is our expectation, basically what we want out of that data. So for example, here, let's say if my data is, let's say X, and suppose Y is a label. For example, this X can be, let's say one image, and Y can be, let's say the class of that image. So what is ultimately what is our goal here? Our goal is basically to learn a function, and that function will take this X as the input, and it will basically map to output that is actually Y. Now, if you see what is basic difference here between the traditional machine learning and nowadays what is happening in deep learning is basically in traditional machine learning, this X was not directly mapped to Y. In between this mapping, basically we had one pipeline. In that pipeline, we had something called feature extractor. So basically that feature extractor part was manually designed in traditional machine learning approaches. So from the data X, actually some features were derived, and then those features were generally used with the machine learning models to predict this Y. But what has happened in this deep learning, this hand design part of this feature is actually have gone away, and this feature extraction has become basically automated through the learning itself. It means that our deep learning models are going to have the parameters. Those parameters will be initialized initially with some techniques. Generally, those techniques relies on the randomness, and then after that, basically, X will be treated as the input to that, let's say, model, and it is going to produce Y as the label. And now, if there is whatever is the output that it is producing, and if that output is not correct, then some sort of, let's say, penalization will happen, and that is generally termed as a loss here. And then that network will try to basically reduce that loss. And that how it will try to reduce that loss, basically network will try to update its parameter in such a way that next time that loss should decrease. And in order to do that update, basically the algorithm that is being used is called stochastic gradient descent, and that generally uses let's say, this parameter update while this back propagation is happening in this, let's say, whole sort of this deep learning models. So I hope that all these things are well covered and all of you are well aware with this type of things. So just this particular let's say session is going to be on top of all these basics. So now, again, coming back to our problem, that suppose if we are having X as the data, here you can think that this image itself is basically our input and this is our data. And then what is our output? Let's say output is basically cat. So similarly, suppose, let's say, we can have one problem where we can have 10 classes. Let's say we can have cat, dog, face, like that. We can have 10 classes. We can have a lot of samples, and we already know that which sample belongs to which class. Then suppose if we are going to basically train a deep learning model or a convolutional neural network by using these images as the input and the class label as the, let's say, labels, basically then this particular framework will be treated as a supervised framework. Similarly, we can have the supervised framework for the object detection also, where our let's say labels can be not just only what are the classes here for these objects, but what is the bounding box here. Basically, what is the location of these objects, that where it is present in the image, and it can be represented by basically 4 values. We can have the coordinate of this top and left corner, and what is the height and width of this particular bounding box. So basically we can use these numbers as the kind of a label or supervision mode basically for this problem. Similarly, suppose if we have a problem of semantic segmentation, then semantic segmentation problem can be also thought as a classification problem, but this is not classification of the whole image. Rather, we can just think that this is classification of single pixels, or basically all pixels independently. So if you take one pixel, then it can be categorized into one of the classes, either, let's say, in this particular case, either it is grass, cat, tree, or sky. It means that for each of the pixels, we are going to have some labels associated with that, and that is basically called the ground truth. So again, we are going to feed some information about that, what is our expectation, what we want out of this, let's say, the processing that we are doing. So if you see, these are let's say the supervised way of learning. Even you can see another application of supervised here, that is image captioning. So suppose if we have an image and we want to generate a caption for the image, then basically again we can train the model in such a way where this image can be the input, and the caption that we are having, from the caption actually we can again project the caption into some higher order feature space using again some different type of deep learning model, which is called basically recurrent neural network, that can be applied over the kind of a timestamp data. And we can use the convolutional neural network on the image data, and we can use the RNN over this text data, and then ultimately we can use the high level features where basically we can take the decision, and based on that basically we can again have the supervision where we can already let's say have what kind of caption we are expecting from these images as a training. Then basically we are feeding some information about our expectation here. So that's again is basically kind of a supervised problem. Then what about unsupervised learning? So in unsupervised learning, we have only data. There is no labels given to us. Means what we want, means what is our expectation from that data, that is not clearly known. So suppose if this is not clearly known, then what we can do with that unsupervised, let's say, data that we have, are basically the data for which we don't have any label. So basically we can try to learn some underlying hidden structure of the data. Means what are the properties that we can figure out in the data, and that properties means it can be in form of that, let's say this part of the data is very similar to this part of the data, or let's say this portion is very similar to this portion, or something like this. If you can find out some correlation between different let's say the data, and that those information, if it can be utilized in order to do some task that we are actually interested. For example, suppose if you want to do clustering. So what is the meaning of clustering here? Suppose if you are given with some data and you want to divide your data, let's say, into some number of clusters, then basically the data which are actually going to be categorized into one of the cluster should be actually sharing some kind of a common traits or some kind of common properties among themselves. So now if you see here, one of the example is k-means clustering, basically that all of you I think should be aware that this is a very basic clustering technique. Similarly, we can have a kind of a principal component analysis PCA, which can be used for the dimensionality reduction, and even after dimensionality reduction, even it can be used further for clustering and for other purposes. Similarly, we can have the generative adversarial network that we are going to talk about this today in this particular session. That distribution learning means can we also learn the distribution of the data in such a way that we can generate new samples in the same distribution. So let's continue our discussion here. So it means that the generative adversarial network problem that we are going to discuss today is basically the basic version or vanilla version of this problem is actually termed as an unsupervised learning problem. So why it is going to be termed as unsupervised learning problem? Because here we are not going to feed any data directly. We are going to feed the data in form of the basically distribution. We want to learn the distribution of a let's say given let's say set of the images that we have. But what is our input there? So input is basically going to be a random noise. And what is the output that we are expecting? We are expecting a new image. We are expecting a new image in basically, and that new image should be very similar to, or it should follow the similar distribution that actually our original data is actually following. Okay, so but before going to this this unsupervised learning of this generative adversarial network, let's just have a quick look over this autoencoder. So now if you see basically what is autoencoder here, so this is an unsupervised approach for learning a lower dimensional feature representation from unlabeled training data. So this is also one kind of an unsupervised learning approach, where now again, if you want to try to learn some inherent features or some important features from the data, then this autoencoder is one type of let's say neural network that can be used basically to learn such features. So now basically what is the let's say what is the structure of this autoencoder? The structure of autoencoder is suppose if we are having let's say we are having some sort of data with us, and that we can refer as a training data. So suppose we have a lot of images with us and that we are referring as the training data, but we don't know what are the class labels or what are the objects inside these let's say images. We don't have any such information let's say along with us. So suppose if this is the scenario, and now suppose if you want to use this data for any particular application, and suppose if we have a huge amount of data, and if you want to make some application on top of that, and because this image data is going to be a very high dimensional data, and then instead of using this high dimensionality data, basically if you want to use some low dimensional representation of this data, then how we can learn that low dimensional representation from this data? So basically we know that we can have a neural network, and that neural network basically we can refer as an encoder. And what this neural network can do, basically that neural network can take an image as the input, and then it can basically transform that image into let's say some kind of a feature. What is the meaning of this feature? Basically it will be some values. These features can be one-dimensional feature. In fact, even we can have two-dimensional feature, we can have three-dimensional feature. It is totally basically it is completely upon us that what type of encoder actually we are using, or we are incorporating, or we are implementing. So based on that, we are going to have, let's say, the dimensionality of this feature. But in general, most of the time, people are generally basically extracting this feature, which is basically one-dimensional data or one-dimensional features. Even it is two-dimensional, generally people just do the stretching so that it will be converted into one-dimensional. So now question comes that, okay, then what is this encoder here? So now, if you are already aware with that what is a neural network and what is a convolutional neural network, then basically this encoder is nothing but it is the same thing. It can be either a neural network, or it can be a convolutional neural network, or even it can be any projection strategy that can project the data into some higher order space, basically in a higher order feature space. So now, if you see, in early days, this encoder was nothing but some combination of linear and non-linear kind of a functions. But now, let's say later, it became basically a kind of a neural network, or if you are aware with something called multi-layer perceptron. So basically, multi-layer perceptron is nothing but that is also artificial neural network, but it has only the dense connections. So what is the meaning of dense connection? The meaning of dense connection is that if you take any neuron in a particular layer, then it is going to be connected with all the neurons in its previous layer. So that's what is the definition of a fully connected layer, or generally also termed as a dense layer. So if you see, in very early days, this encoder can be thought as a very basic functions, a combination of some linear or non-linear function, or basically we can say some kind of a projection function. Later on, if you see, around from 2000 to, let's say, 2015 or so, in this particular let's say time frame, basically this encoder can be thought in terms of basically let's say deep neural network, basically that will have a kind of a these fully connected layers, because deep neural network is going to have the data, input data is required in one dimension form. It cannot take input data in a matrix form. Then basically, whenever you are going to use let's say the traditional version of neural network, or now we are terming it here as a new, let's say, multi-layer perceptron, then basically you have to transform your data into one dimension, then only you can use it. But now, if you see nowadays, basically this encoder is very let's say the latest one is it is nothing but it is a kind of a convolutional neural network that can take image directly as the input, because this CNN is basically designed in such a way that it can take image or video or basically matrix type of data. It can take directly as an input, and it can finally transform that input into some higher order feature space, and that higher order feature that it is basically producing, that feature can be used with any of the classifier, or basically any of the, let's say, objective function. It can be used in order to basically do any task. Suppose if it is classification task, then basically that feature can be used with any classifier. That classifier can be even let's say it can be a support vector machine, or even it can be, let's say, some latest classifiers that people are generally using, which is basically nothing but some called softmax classifier. So it means that now basically if we have a set of data, basically we can transform that data into feature space using a convolutional neural network. But now what happens actually? What is the problem here? There is only one problem. If we are going to have a convolutional neural network, then initially the convolutional neural network is going to have a random weights, because suppose if convolutional neural network initially is going to have a random weights, then the feature that we are extracting might be meaningless. It might not have any correlation basically, or it might not be a good representation of our input data. So it means that, and we know that whenever this convolutional neural network or any sort of these deep learning models are generally used, then basically we have to have some objective function, and that objective function is basically going to give us the information representation that whatever is being produced by this convolutional neural network, how good representation it is. If it is not good, then basically it is going to generate the loss, and then the network will try to reduce the loss by updating its parameters. So, but this update of parameters can only happen if we are going to have some objective function or some loss function. And loss function means basically that something we are producing, how good it is for our application. So now, in this particular setup here, suppose if we have an input data, we have the encoder, which is nothing but, let's say, a convolutional neural network. Here, ReLU is nothing but this is a kind of activation function. You can simply think it as a convolutional neural network. So ReLU is a part of this CNN here. So now basically this feature is extracted, but now what is the guarantee or how we can judge that the feature that we are extracting from these images, how good it is, basically how good or how well it is representing our actual input. So because in the current setup, if we only have encoder, then it is not possible to judge the goodness of this feature. Then what can be done here? Basically, then we can have one more network on top of this feature, and that network will try to reconstruct the original input that we have from the feature itself. So it means that, so just one thing here, that this feature basically in higher order space, it is generally having the lower dimensionality than the our original input that we have in the image form here. And what is our ultimate goal here? Our ultimate goal is we have to basically generate the features that should be a very good representation of our input image. It means that it should capture all the meaningful information that basically contained by our input data. So that's what is our goal. But in the current setup, our goal is this. But in our current setup, that goal is not reflecting, because see, if we want that the feature that we are deriving, it should be let's say representation of our input. But if it is not a good representation of our input, then how we will come to know? So there is no way in the current setup here to measure that how good it is. So that's why what we are going to have, basically, in order to learn this feature representation, basically we are going to have one more network here, and that network is going to be termed as a decoder network. And what this decoder network is going to do, basically, this decoder network will take the feature that we have extracted as the input, and it will try to reconstruct, or it will try to basically generate the original input image from where actually we derive this feature. Then what will happen, basically, once we are going to extract this, let's say the image reconstruction, once we are going to reconstruct this image, then basically what is the next task? The next task, we can now very easily, we can quantify the goodness of our whole approach here, that how close this reconstructed input data with respect to our original input data. So it means that, suppose if this x prime here, or basically x cap here, which is the reconstructed data, if it is very close to this input data, then we can say our model is very perfect here. It means that the feature representation that we are going to have is actually capturing very meaningful data from the input, and that's why by using only those features, we are able to reconstruct our original input data. So it means that, and now then what could be this decoder? So again, decoder is also going to be a neural network. Again, if you see in the traditional setup, it can be a kind of some kind of a projection matrix, not matrix, some kind of a, let's say, projection function. And even we can have let's say we can have a kind of a deep neural network also. But in the present scenario, or in the latest thing, we can have this decoder as again kind of a convolutional neural network. But hold on, if you are aware with convolutional neural network, then you should get confused here, because generally convolutional neural network take input image, input as the image, and produces basically some class labels, or basically some feature representation. But here we are talking about, this is a spatial convolutional neural network, which is generally termed as a up convolutional neural network. And what is the meaning of here up convolutional neural network? That it can take basically one-dimensional input as one-dimensional feature as the input, and it can produce an image as the output. So that is also possible using convolutional neural network, but that type of convolutional neural network is basically termed as a up convolutional neural network. So it means that, so now basically we have a, let's say, training data, but we don't know what is the label of the data. But we can have some sort of encoder, and that encoder is going to project all these data basically into some higher order feature space. And then we can have a decoder, and that decoder will take those features as the input, and then it will try to reconstruct our original data. So it means that even this is unsupervised, but now actually we are generating some sort of technique here by using which actually we can measure that what is the goodness of all our this encoder and decoder functions are basically this network that we are going to have. So it means that what we are going to do now, we are going to simply compute that what is the loss between the original input data that we had and what is the reconstructed input data. And this loss can be let's say L1 loss, L2 loss, we can have any loss function. And then basically what we can do now, we can just do the back propagation of this objective function that we just derived here. And this back propagation will happen of the decoder network as well as encoder network both. It means that, so this is going to be a forward pass. In forward pass, you are giving basically you are having the input data as the input to your encoder. It will produce the feature. Then that feature will be input to the decoder. It will produce the let's say reconstructed data. Then we will measure that what is the loss between the original data and reconstructed data. And then that loss is basically going to be back propagated, and back propagation means we are going to update the parameters of decoder and encoder such that next time this reconstructed data will be even more closer as compared to the input data, and this loss will decrease next time. So suppose if we are going to just do multiple runs like this, then after some time we will find that this reconstructed data will be very similar to the original data and loss will get decreased. And then once this model is going to be trained, then basically we can throw out this decoder part, and we can only have the encoder part, and then we can have any input data, and we can basically extract the meaningful feature Z from that input data using encoder, and then that these features will be used basically for different problems. So now if you see this is basically if you see there is no label at all, we are having input data, we are again reconstructing back the same data and we are generating the loss. So that's why this label is not required. So after training, we will throw away the decoder part. We will have only encoder. Then now suppose you are going to have some, let's say, a test data, or even so, now you want to use this particular trained model for any application. Then what we can do, we can have some classifier on top of this feature. We can do again some fine tuning, and basically after doing this fine tuning, basically we can have this as a let's say network, and that is going to basically give you some better result here. Now if you see why actually I explained this autoencoder, because this is going to have some relation with generative adversarial network. If you see autoencoder is still, it is going to be very simple. Why it is going to be very simple? Because we have some input data, we are deriving features. From feature we are reconstructing data. It means that we know that how we can measure the goodness of our whole strategy, and based on that we can update the parameter. But what is going to happen in generative adversarial network? So in generative adversarial network, basically we don't have any input given to us. We only want output. There is no input given to us. We only want output. And what output we want? We want a new sample. We want a new sample basically that is going to be generated. Basically that should follow the training distribution, or that should follow the data distribution of our training set. But what is the input that is given to us? Nothing. There is no input. So if there is no input, then from where to generate, what to generate? And even if you are generating a new image in our training data, suppose even if you are coming with some strategy to generate some new image in our training data, how to measure that the image that we have generated is how good it is? So again, so there are going to be two challenges here. One challenge, if there is no input data given to us, then what input we should consider? This is one challenge. And another challenge, even suppose if we are generating some new samples by some mean, then how we can measure that whatever sample we have generated, how good it is? So because if we can measure, then only we can update the parameters to make to generate even images in later phase of the training even better and better. Okay, so now if there is no input data, then what generative adversarial network is saying that suppose if you are going to have a network, and if network is generating a new sample, then if you are running your network multiple times, then it should generate the different samples. Means if I am running my network, now it is generating one sample. Next time when I am going to run the same network, the next time it should generate a different sample, not the same sample. Suppose if it is going to generate only one sample always, then it is not going to be meaningful. So if you run 100 times, then it should generate 100 different images. So it means that if you want to generate different images, then we have to bring some sort of randomization in our network, and that's what is the strategy that is followed by Anne Goodfellow in his basically this generative adversarial network framework. So now what is the approach? The approach here is, if there is no input, but we want to generate samples and we want to generate new samples every time, then let's have some input, which is basically some random values. So it means that basically here we are going to have some random noise, are basically termed as some random values of we are going to have a single vector, and the values of that vector is going to be basically derived randomly, and that will be the input to our network. And this network is nothing but this is called the generator network. What is generator network? We are coming to it quickly. So but now what is happening here? So now basically we are basically hypothesizing that we have a network, and that network has a capability that if you give a vector as the input, and it is going to produce basically an image as the output. We have already seen such type of network, so that's why basically I covered this autoencoder here. So if you see, what is this decoder? It is taking one-dimensional input, and it is basically producing an image as output. So basically, if you see here, this generator network is very similar to the decoder network that we have in autoencoder, that it is going to take one-dimensional as an input, and that those are random values, and generating an image as the output. Now, suppose if this generator network is already trained, then if we are changing our input with random values, then the output that it is going to generate will be different output values. But it means that now we can have a generator network which is very similar to the decoder network. It means that we can use up-convolutional neural network as a generator network. We can use up-convolutional neural network as a generator network that can basically transform a one-dimensional input data, that is basically random values, into an image. So this particular part is understandable because we just saw the same mechanism in our autoencoder. But now question comes, in autoencoder, actually the decoder was the second part, but here this decoder, or basically now it is termed as a generator, here is the first part itself. So now again second question is coming that, okay, so now if we are able to generate a sample, an image from this random noise using this generator network, how we can measure what is the goodness or how good this particular image in our training distribution that we have? Because now if you see, so far we have not used our training sample at all. We are having a generator network that is basically nothing but a up-convolutional neural network. Our input is a random vector, and it is generating some output as the image. If you see, initially, again, if our generator network is initialized with random values, then whatever output we are going to generate will have the random values. It means it will generate a random, basically going to generate a random matrix as the output. So if you visualize that as an image, obviously we will not have anything that is from our training samples, because we have not utilized any information from our training samples so far. So it means that now we have to do something such that we can guide this generator network in such a way. We can guide in this generator network such that this generator network should learn that what is the training distribution in our training data, such that whenever it is going to generate a new sample here, it should generate in the training, it should follow the same distribution that our training set has. Then only it can generate the samples which is very similar to our training data. So in order to basically do this guidance, this generative adversarial network is basically having a two type of network. One network is generator network that we just saw. So this is generator network, which is basically generating a new sample. But on top of that, we are going to have one more network that is called actually discriminator network. And this discriminator network is nothing but this is a simple convolutional neural network for a two-class classification problem. And what this discriminator network is basically going to do here. So now again combining this generator network as well as discriminator network in a single picture, here you can see. So this particular part we have already seen here just in the previous slide, that if we have a random vector as the input, our generator network will generate, let's say, different images corresponding to that input. But those images which is actually generated using the generator network is actually termed as let's say the fake images here, because this is not the original image, or this is not the real image, this is the generated image by the generator network. But now the problem here is that originally our generator network is not guided, it has random values or random parameters. Then this fake images that we are going to generate will be also very random. Then what we can do here, how we can guide this generator network such that it should follow basically the training distribution of our real images. Then in order to do that, basically we are going to have this discriminator network on top of the output of this generator network. So generator network output is basically the fake images, or you can say generated images. And we also have our real images. Basically this is our real training set. So now what we are going to say, that the task of this discriminator network is, if it takes any fake image as the input or any generated image as the input, then it will classify that input as a fake image. But if we generate any original image, but if it takes any original image as the input, then it will classify that original image as a real image. Basically, now what is going to happen here, this whole let's say training is going to happen kind of a two-player game, where generator network will try to basically try to do something with the objective function that we are going to derive, and the discriminator network actually is also trying to do something which is going to be basically opposite. Or in other words, how these two-player game are basically why it is called two-player game. Basically we are going to have two network. One is the generator network and another one is discriminator network. Now at a very ideal level, what we are going to do, let's say with the generator network, now we are going to guide this generator network in such a fashion that whatever output this generator network is basically producing, now the output, if these output are going to be taken as the input by discriminator network, then it should be classified as a real. That's what is the objective of this generator network. Now we are going to frame the whole objective function in such a way that generator network will try to produce a very nice output, or the output which should be very similar to real image, such that it can fool the discriminator network, such that discriminator network should think that this is not the fake image, this is real image, and it gets fooled. That's what is the objective of this generator network. But at the same time, what is the objective of discriminator network? The objective of discriminator network is to learn itself in such a way that let's say even if the generator network is producing even a very good let's say very nice image, still this discriminator network wants that image to be classified as a fake, because actually it is generated image, it is not the real image. So it means that now what we are going to do, we are going to frame the objective function for this generative adversarial network. In that objective function, there is going to reflect two things. One thing, what will reflect that generative network wants to produce such an image such that it can fool the discriminator network. At the same time, discriminator network wants to have an objective function in such a way that it should not get fooled by the generator network. So it means that now this is going to be kind of a two-player game where each network is trying to fool each other, basically other one. So now this is just another way of interpretation of this whole generative adversarial network here. So now Suppose if we are going to have our original training samples, then original training samples are only going to be seen by the discriminator network, and discriminator networks want these original samples to be classified as the true, or basically to be classified as the original. It means that the final probability that it is, because this is a two-class classification problem, then basically we can simply have basically the probability as the output. So basically the final probability that it is going to produce should be towards 1 for all these images, which is actually real. But what is going to happen with the fake images? So now we are having the input noise, which is given as the input to the generator network, and generator network is basically producing let's say fake images, or generating fake images. Now those fake images also given as the input to the discriminator network. But now in this particular let's say series here, when the generated image is the input to the discriminator, then what is the objective of discriminator is to classify that generated image as the fake. That's what is the objective of this discriminator. But what is the objective of this generator? That this discriminator should classify this generated image as the true one, or as the real one, not as the fake. It means that suppose if G is generator, if Z is the input, and then GZ is going to be the generated image, and D of GZ is basically going to be the output of the discriminator if the input is the generated image. It means that now what discriminator wants the output, or basically the probability of this discriminator to be classified as a real is going to be basically 0, means it should be fake. It means the probability for classifying as a real should be 0. But at the same time, what G wants, what our generator wants that the probability of basically this generated image to be classified as real should be let's say the maximum possible, that is near to 1. But what discriminator wants, that it should be near to 0. So now combining these both objective function that we just discussed, or the idea just writing into a mathematical formulation in form of a objective function, then this is going to become a kind of a minimax objective function. And now if you see in this objective function, basically what is the task of this objective function? The task of this objective function is that whatever input we are going to have, it is going to produce the likelihood of the real image. It means that likelihood of real image, it means that if it is actually a real image, then it should be towards 1. If it is not a real image, then it should be towards 0. But now if you see what kind of objective function, or what is the mathematical formulation here. So basically we are going to have log of, so this D is nothing but it is representing discriminator. This theta D is nothing but this is representing the parameters of the discriminator. Here X is going to be the input to this discriminator, and X is basically, if you see here, this EX, basically this P data is nothing but this is sampling. So sampling of X from the original data. So basically this X is the original data. So now if you have original data and we are feeding directly to the discriminator, then what discriminator wants? Discriminator wants this particular output to be towards 1. If this output has to be towards 1, then log of something which is going to be towards 1, basically basically what we want to do now, basically we want to optimize this objective function, or if you are talking in terms of the discriminator, then basically we want to maximize this objective function. So that's why if you see for theta D, or basically for the parameter of discriminator, basically this is kind of an let's say maximization problem, which is nothing but maximizing the likelihood of the real images using the discriminator. Similarly, at the same time, we also know that what discriminator also wants one more thing, that if there is the input which is actually not the X, but which is actually the generated image. So now suppose if we are going to have the input which is basically G of Z. So now G is the basically generator, theta of Z is nothing but parameters of the generator, Z is the input random vector that we gave as the input, then this G of Z is nothing but the generated image. So if suppose if we have the generated image as the input, but discriminator is basically giving the likelihood for the real image, image, it means that if it is the generated one, then instead of 1 it should be 0, but d of gz is going to be the maximum, is going to basically increase increase the likelihood for the real image, but actually it has to be let's say fake from the discriminator points of view. So that's why instead of, let's say, log d of gz, it is log 1 minus d of gz, because now actually basically it is going to maximize. Now 1 minus d of gz is going to maximize, basically it's going to maximize the likelihood of being fake this image that is actually the input to this d from the perspective of this let's say discriminator, because actually this is a maximization problem. So this is a maximization of likelihood. This is a maximization of likelihood of original data as original. This is maximization of likelihood of, this is basically maximization of likelihood of fake data as a fake from the perspective of this, let's say, discriminator. But at the same time, what our generator wants, so this is the parameter of generator. What generator wants that this fake image that is generated should be classified as a real image. It means that basically it wants the output of this d of gz should be very close to 1. So if it wants it should be very close to 1, it means that it means that 1 minus something which is close to 1 has to be close to 0. It means that now the same objective function that we have, if we think from the perspective of the generator, then from perspective of the generator, it is not a maximization problem, rather it is actually a minimization problem. Why? Because what generator wants that d of gz has to be close to 1. It means 1 minus d of gz has to be close to 0. It means that this is a minimization problem from the perspective of the generator. So that's why this is a minimization problem over the parameters of generator, but maximization problem over the parameters of discriminator. So it means that discriminator wants to maximize this objective function such that d of x has to be close to 1 and d of gz has to be close to 0, whereas generator wants to minimize this objective function such that this d of gz should be close to 1. And that's what basically we discussed at the idea level also. And the same idea is now incorporated in mathematical form in this minimax objective function. So basically, and now what is going to happen using this minimax objective function, this discriminator and generator is going to be basically updated, back propagation will happen. And because if you see this discriminator is a maximization problem, then gradient ascent will be used there, and basically generator is a minimization problem, then gradient descent will be used here. But in practice, this particular formulation has one problem. It actually leads to some convergence issue. And why it leads to some convergence issue? Basically, what happens when we have this minimization problem over generator, then what happens basically, if you see in generator, initially when our training is starting, then the parameter of generator is basically random values. Then initially the samples that this generator is actually generating is actually let's say 2 away from the original samples or real samples. It means that originally the training has to be very fast, or this network weights has to be updated very fast, such that it should learn quickly that what is the distribution of our original training data. But suppose if we are just going to plot that, okay, what is this objective function of this generator with respect to what is the likelihood of this discriminator. So now if you see basically this log 1 minus, this is going to be the basically this likelihood function that we are going to have here. Suppose if we are having our objective function with respect to this in terms of the probability, basically if you see this d of gz is nothing but the probability of discriminator of basically classifying a generated sample as a real one. So what is the probability that a generated sample is going to be classified as a real one? This is the output of this dz. So what happens here in the initial run, when the samples which is generated by the generator is basically very random, then the probability of being classifying those random samples as the real sample is very less. And when the probability is very less, at that time, if you see this whole function is very flat, then basically there is very less amount of gradient available. If you take the first order derivative, then because when we are going to update the parameters, then it is going to rely on the first order derivative. So if we are going to take first order derivative here, then the first order derivative will be very close to 0. It means that the update of the parameter of generator will be very slow in the initial phases. But actually in the initial phases, our learning has to be boosted, but that is not going to happen with this objective function, and it then basically it leads to some convergence issue. So that's why in practice generally for generator, instead of using gradient descent, even for this also gradient ascent is used. But when we are going to use gradient ascent, then this minimization problem will become a maximization problem. And when this minimization problem will become a maximization problem, then basically instead of writing log 1 minus, we can just remove this 1 minus. We can simply say log d of gz, because both are going to be basically same. If we minimize log 1 minus d of gz, or if we maximize log of d of gz, both are going to give the same, let's say, same kind of effect. So in practice, what happens basically, instead of gradient descent, this is also going to be gradient ascent. And then you can see that this is a new function here, which is basically, this is for minus log of d of gz with respect to this probability. So now if you see, when probability is very less, it means that in initial phases, now generator is going to learn quickly because we have enough gradient here. Basically, you will get, let's say, better kind of updates in your parameter during back propagation. Then your generator is going to learn quickly that what is the distribution of basically your training data. So this is just a GAN training algorithm that is just represented here, that we are going to sample, let's say, vectors from the noise, and then we are going to sample the images, basically that is real images, and we want to basically have the objective function. We will apply stochastic gradient ascent, basically not descent here. This is ascent because this is a maximization problem over the discriminator. And similarly, we are going to do the similar thing for the basically generator also. So this one has to be basically modified in the practice. This is a minimization problem here, but in practice, generator is also basically implemented as a maximization problem by removing this 1 minus here. This is something called k steps here. So there is no fixed rule here, but for different problems it will have different values. So this is kind of this hyperparameter. So now what is going to happen? So now we have this objective function. Using that objective function, we are going to train basically, or we are going to update the parameters of generator as well as discriminator networks both. And once we have updated and our training has been done, then basically we don't need this discriminator network, let's say, for future. So again, like if you see in autoencoder, once model is trained, then decoder is not required. Similarly, in generative adversarial network, once model is trained, now this discriminator network is not required. Now we can have only the trained generator network. Now you can give any random input as a random noise as the input, and it is going to produce an image as the output. And because this generator network has basically inherently, it has learned that what kind of basically input images it should produce, such that discriminator network can be fooled. And discriminator network can be only fooled if these images which is generated by generator network is very similar to the real images. It means that in this training process, it has already learned that what is actually the training distribution of the data. So it means that even if you don't have discriminator network, once your model is trained, you just give as a random input as a random noise as the input, and it is going to produce an image as the output. And then basically that image will be very similar to images that we have in the training data. It is not going to be exactly same the image that we have in our training data, but it will be very similar. For example, suppose if you have a lot of cars, it will generate a new image that will have a car, and there will be some variation with respect to the existing images, but overall it is going to follow a very similar appearance. So these are some generated images here. So if you see, these are generated images over MNIST dataset. These are generated images over Toronto phase database. These are generated images using very simple GAN model. So that's why if you see, these generated images are not very good, but still it is trying to basically learn what is the training distribution. Similarly, these are generated images over CFAR10 dataset. But now if you see, still the quality of these generated images are not very good. So in order to get rid of this, basically this generative adversarial network was basically enhanced in 2016 with deep convolutional generative network adversarial network, where basically the generator was, let's say, deeper network, and this generator was a deeper network with upsampling network that has the fractionally strided convolutions. Basically all the let's say unpooling and pooling things got removed, basically got replaced with the fractionally striated convolutional. Similarly, the discriminator network was also a deep network, basically, that can basically discriminate between the generated image as well as real images. So now, after doing this DC GAN, basically, there are some let's say other aspect, there are some other deviation in this DC GAN, that all pooling layers were basically replaced with striated convolutions and fractional striated convolution in generator. Batch norm was used in both the generator. So batch norm is basically one kind of a regularizer in order to increase the generalization ability of the network. And they removed all the fully connected hidden layers for deeper architecture, and used ReLU activation generator for all layers except the output. For the final output, TANS is used, because TANS is going to give you the output between -1 and 1, but ReLU actually kills all the negative inputs. And use leaky ReLU activation in the discriminator for all layers. So these are some changes in this let's say DC GAN. And now if you see, this is the result that is produced by this DC GAN. So if you see, the quality of these images are really very good. And if you see, the model is trained on let's say images, basically you can see these are images like bedroom scenarios. And if you see, the images that is generated here is giving clear-cut let's say information that these images are basically generated for some bedroom scenarios. So now this is about this generative adversarial network, and it means originally this generative adversarial network was proposed basically to generate new samples in our training data. But what happened, slowly people also use this generative adversarial network concept even to use or even to perform an image-to-image translation problem. What is meaning of image-to-image translation? That if we have an input image in some other domain, and if you want to transform that input that image into some other domain, then basically we can use the similar concept of generative adversarial network. So what can be done here? If you see, in the original generative adversarial network, our input is a random, let's say, noise vector. And we have an up convolutional neural network that can transform that basically vector into an image form. So now in image-to-image translation, basically what we can do, we can replace the input that was the basically this input noise. We can replace that with the image that we have in domain A, and then basically the generator can produce an image in domain B by having the image of domain A as the input. Then obviously there has to be some changes in the generator network. Then basically that generator network can be an autoencoder. So what we can do now, basically we can replace, if you see, in generative adversarial network, the generator network was nothing but kind of a decoder part of autoencoder. But now in image-to-image translation, we can use the whole autoencoder itself as the generator network, because we know that autoencoder is one type of network which can take an image as the input, and it can produce an image as the output. So it means that, and we want a similar scenario here in image-to-image translation, that we have an image in some domain A as the input, and we want to transform that image into some another domain B as the output. So if you see here, we are going to basically, I'm just going to give you the overview of three, let's say, two well-known models, basically, that is called conditional GAN, or basically also referred as pix-to-pix. And one very important technique is called cycle consistency, let's say, adversarial network cycle GAN. And this is, last one is actually our work that we have done, perceptual cyclic synthesized adversarial network. I will just give a quick overview of these methods, and then after that, I will also let you know that what are different type of applications, basically, where such type of image-to-image translation techniques are actually useful, and people are basically doing a lot of work in those areas. So now, before going to this conditional GAN, basically that is pix-to-pix, suppose if we have to use the same concept that we just saw of generative adversarial network, but not for generating the image from the random vector, rather if we want to generate image from another image. So now again we can have the same scenario, that we can have a generator here, but now this generator is not going to be only up convolutional neural network, rather it can be a full-fledged autoencoder network, basically, which can can take an image. Let's say this is in domain A. Basically, this is nothing but the sketch of shoes that is in domain A, and the shoes itself in the, let's say, with all texture as well as color information, that is going to be basically, let's say, in domain B. So suppose if we have any sketchy image and we want to generate that what should be, let's say, the equivalent actual image, then we can have a generator network basically, and that generator network can take this one as the input and it can produce here as one of them as output. But now again the same question will come here, that this generator network initially it is going to have, basically it will have two things. It will have encoder as well as decoder, and because this generator network is going to have encoder and decoder, then the weights of these encoder and decoder initially is going to be the random values. And when these weights are going to be the random values, then the kind of image that we will generate initially, we will not have a very good image here. Then again we are going to do the same thing, that whatever we have generated will pass to the discriminator, and we will also have the real images corresponding to this particular, let's say, the sketch image that we basically we are using as the input. So basically this is as the input, and let's say this is the counterpart, let's say original image that is also given to us. But we are generating directly, generating directly for using the generator. Obviously it is not going to be a very good image, but then what we are going to do, we will treat this one as the fake image or generated image, and we will also have the real images we will pass to the discriminator. And again we are going to have the same objective function, that this generator wants this discriminator to classify this generated one as a real, and but at the same time what this discriminator wants this generated one to be classified as a fake and the real one to be classified as a real. Then again we are going to have exactly same objective function that we had for our original GAN model. And basically we can perform this back propagation, we can perform the training, and once training is done we can throw out this discriminator part. All these things are not required. Then if you have any sketch of a shoes basically, then we are going to generate that how these shoes will actually look like. Obviously this is not going to be let's say it is not going to be a unique output that what we are looking for. Even it can be, there might be a lot of variation in the output that we are going to generate, because this is a kind of a problem of one to many. Because suppose if we have a sketch of shoes like this, then there can be unlimited number of shoes that can give basically the exactly same sketch. So that's why this is kind of a one to many projection. But even in this one to many projection, we want to put extra constraint by showing that okay, our whatever image you are generating, those images should be very similar to this image. So that's what is one of the constraints that we are even inserting here in order to reduce basically the search space, or basically the projection space that we are going to have using this generator. So now here, if you see, this is basically a vanilla. This is basically the vanilla version of this generative adversarial network. Now this basically the generative network adversarial network is enhanced in 2017 by this Philip. Basically that is called pix-to-pix model or conditional GAN, which is very popular. So what is this conditional GAN? So conditional GAN is basically having one condition at the discriminator network. So if you see, everything is very similar to the normal GAN, that we have an input, we have a generator, it is generating one let's say fake image, and we have real image, and we have discriminator wants to basically discriminator is taking the input as a generated one as well as a real one. If it is real, it wants to classify as a real. If it is generated, it wants to classify it as a fake. But what this conditional GAN is doing, because this is let's say kind of a projection from X to GX. So even if you see in initial phases this GX might not be very similar to Y, then actually this generator is not going to basically learn very quickly. Then what it is going to do, this conditional GAN, the actual input that we have used, that is going to be treated as a kind of a condition. And when we are going to feed this generated image or original image to discriminator, then along with that we are also feeding that actually what was our input image, only for the reference purpose, that okay, this image that we have generated is basically corresponding to this original image. Even the generated image is not very good, still we are going to have very nice let's say information from our domain A. And if you are just going to combine these two and going to give the input to the D, and the same input is also going to be combined with the real output, the expected output, and basically it is going to be basically fed in this discriminator. So now if you see, this is a very simple change here in the conditional GAN, that when we are going to feed, let's say, either generated image or the original image to the discriminator, we are going to have the input image also as a kind of a condition, even just to give some extra information, let's say, to the discriminator, such that it can basically better do this, it can better differentiate between the generated image as well as the original image with respect to the input image that we have. So again, this is the similar thing, just conditional GAN, that we suppose if we want to translate, let's say, basically this sketch to the real image, then we are going to have generator is going to transform into the real image. We are going to have the original sketch as the basically condition here when we are going to use the discriminator network. If you see, these are some sample outputs of this pix-to-pix model, are basically conditional GAN model. So here, basically, this is labels to street scene. Suppose if these labels are given as the input, and we want to produce this actual output, that how it is going to look like, and then model is going to train basically. Then this is domain A, this is domain B, and projection will be from domain A to domain B. So now if you see, it is able to produce very nice output here. Similarly, if you see other cases, like this is labels are given, and this is going to be basically projection to the let's say facet, or basically the structure here. This is projection from black and white picture to color one. This is projection from let's say aerial view to kind of a map here. This is projection from day to night. Similarly, we can have night to day. It is another projection. This is projection from sketch to let's say the actual image or the color image. So now if you see the quality of images that is generated from domain A to domain B, that is very appealing using this conditional GAN or pix-to-pix. So these are some more let's say examples, and we have ground truth also. That suppose this was the input and this was the corresponding ground truth, and this is the generated one. This was the input, this was the corresponding output, this was the generated one. If you see, generated one is not going to be exactly same as the ground truth, because when we are going to have the projection here, then it is very difficult to produce exactly same thing, because the parameters are going to be basically parameters are going to be same after the training for all different images. We are not going to have different parameters for different test images. We are going to have exactly same parameter for different test images. So this concept of this this GAN model for image to image translation is further extended to something called cycle GAN in 2017, and that became a very popular model that is called cycle GAN. So now if you see, when we are saying that we have a projection from domain A to domain B, then we know that this can be let's say the projection space can be very high, because we can produce anything in domain B. So in order to reduce the space of the projection, or if you are going to reduce the space of the projection, then basically our projection will be more accurate as per the, let's say, whatever we are looking for. The deviation from our let's say expected output will reduce. So in order to let's say have more constraint on this let's say projection space, the cycle GAN is basically going to use two generators. One generator is going to basically generate one generator is going to transform let's say images from domain A to domain B, and whereas another generator is going to transform the basically from domain B to domain A. Basically, just for example here, suppose if you are generating, let's say, this input and this is the output, then again we will have one more generator that will work in backward direction. It will take this generated output as the input, and it will again generate this input as the output. So it means that now it is a kind of a cycle. We have an image as the input, we are generating an output in another domain, then that output we are again treating as an input with some other network, and we are again trying to reconstruct back the original input that we had. It means that it is again going to be basically kind of a cycle, and then we can have again the loss between what was the actual input and now what is the input that we have basically cycled here, or basically we have reconstructed. That's why its name is basically called the cycle GAN. So here you can see, so from X we are generating this, let's say, Y cap, and then from Y cap again we are trying to reconstruct X cap here. So it means this is generator 1, this is generator 2, or this is basically forward, this is let's say from domain A to domain B, this is back from domain B to domain A. Similarly, the same thing is going to happen even in other direction also, that we will take the input from domain B and we will generate we will reconstruct, or we will generate the let's say output in domain A, and then that output is again going to be taken as the input for this generator, which is actually from A to B, and then again we will try to reconstruct in the domain B. Then again basically this Y cap is actually recycled version of Y. Then we can generate the loss between that Y dash has to be very similar to Y. Similarly, this X cap is basically reconstructed version of X. Then it both has to be very similar. Then we can find out that what is the loss between these two, and that loss is basically called the cycle consistency loss that is actually included in this cycle GAN. This is again the same thing that suppose if we have an input in domain A, then there is a generator A that is basically transforming from A to B. Then now basically it is going to generate an image in domain B. But then whatever we have generated in domain B is again going to be used by the generator. Basically this generator is generating from domain B to domain A. Then basically it will generate the cycle version in A. And this is the original input, this is the cycle version. And then basically we will have the cycle loss here. Similarly, we can have the input from the domain B also, and then there will be generator that is generating from domain B to domain A. Then basically we will generate the images in domain A, and then the generated image is basically will be used by generator of A to B. Then we will again have the cycle version of B, and then again we will have basically cycle consistency loss between these two. Similarly, we are going to have the two discriminator, because actually here we are going to have two generator. One is from domain A to domain B, and another generator is from domain B to domain A. Then basically we are going to have two discriminator also. One discriminator will be at the side of domain A, whereas another discriminator will be at the side of domain B. So at the side of domain A, basically if it takes the original input, then basically it will try to classify this one as the original one. But if it takes the generated one as generated from B to A, if it is going to take that one as the input, then it will try to classify that one as a fake one. Similarly, discriminator B, if it is going to take the actual input from the domain B, then it will try to classify as the original one. But if it takes the generated in domain B, then it will try to classify as the fake one. So again, we are going to have, let's say, objective function for this. Then there will be one objective function for this generator, one objective function for this generator, one objective function for this discriminator, one objective function for this discriminator. So basically, the number of objective functions will be increased now. And now if you see, the output of cycle GAN is very attractive here. And in fact, the cycle GAN is not exactly paired. What is the meaning of paired here? So what is the meaning of paired? Means that if we have an input and we have an output, then both are going to be basically of same scale and same orientation, are basically same appearance. But in case of unpaired, even we can have the deviation in domain A and domain B. So now if you see here, in case of this cycle GAN, basically this is called, this is generally proposed for this unpaired data. So even if you have some kind of unpairing, even exactly if scenes are not exactly same, still it is going to work. And if you see the kind of output that it is generating, basically, let's say this is from domain A to domain B, and this is domain B to domain A, then the quality of images, if you see generated images, are going to be very good. So now on top of this, basically we have also done one work, and that work is basically called perceptual cycle synthesized generative adversarial network. So now basically we have applied this particular let's say GAN model for one of the application of generating the let's say RGB image with respect to some thermal image or NIR images. So now again we are going to have basically the framework of cycle GAN. So in framework of cycle GAN, let's say if we have this image as a domain A image, so this is generated image basically in domain B that we are terming as a synthesized image in domain B. Then we can take the synthesized image in domain B, and we can have another generator, that is the backward generator, and we can have the cycle version again in domain A. Similarly, we can have a real image in domain B, and we can generate a synthesized image in domain A corresponding using the second generator. And the same synthesized image we can use with, let's say, with the first generator, and we can again have the cycle version basically in domain B. So now if you see a cycle GAN is basically, cycle GAN is using the loss between what is this real one and what is this cycled one here, and what is this real one and what is this cycled one here. But it is not able to basically find out, or it is not able to utilize basically the kind of a correlation between this real one in the domain A as well as what is the synthesized one in domain A. So cycle GAN is only having the constraint on this real and cycle. It doesn't have any constraint on real and synthesized here in the same domain. Similarly, this real and this synthesized, it doesn't have any let's say any correlation here. So this particular gap we have identified, and based on that basically we have included some kind of a, let's say, loss function that is in between the real as well as the synthesized one. We have included a kind of a, let's say, this L1 loss, as well as at the same time we have also included a kind of a perceptual loss. What is meaning of perceptual loss? The meaning of perceptual loss means the loss is not going to be computed in the images, in the directly over the images. Images will be transformed into some feature space using some feature extractor, and basically the let's say loss or the differences will be computed in the feature space. So that's why if you see this FE here, this FE here is nothing but a feature extractor, and we have simply used a trained convolutional neural network, which is nothing but VGC16 model, basically as a feature extractor. So basically we will use this synthesized image and real image as the input of the feature extractor. We will get the feature, and then we will find out that how close these features with each other. If it is not close, then basically loss will incur, because whatever is the synthesized image in domain B and what is the real image in domain B, both should be very similar. So now if you see here, the same thing we are going to do in the domain A also, that we are going to basically compute. We are going to compute in between real as well as the synthesized one. So basically we are going to have these two losses. So we are going to have one synthesized loss and one perceptual synthesized loss. So these two losses are going to be increased in perceptual cycle, basically in cycle GAN, and basically we have termed this as PCS GAN, perceptual cycle synthesized generative adversarial network. And this work has been already published in Neurocomputing Journal. And if you see these are some outputs. Basically, these are the input images. These are outputs that is generated using pix-to-pix or conditional GAN. This is using dual GAN. Dual GAN I have not discussed, but it is very similar to cycle GAN. And this is output using cycle GAN. This is output using basically our proposed PCS GAN. And these are the ground truth images, are basically the target images. So even you can see very easily some artifacts that is actually present in the produced images using other methods. For example, here if you see this color is completely gone here, and even in this case also we cannot find. So basically if you see the colors are not properly basically preserved, whereas when we are going to have this perceptual loss on the synthesized and original images, then basically we are able to preserve these color information as well, and even it is going to also preserve the structure let's say in a better way as compared to the existing approaches of these GAN methods. Even we have also computed some sort of let's say quantitative let's say evaluation measures here, like SSIM, which is basically a very general things to compute as a metric in case of any image-to-image translation model, which is nothing but a structural similarity index measure, means how well the structures are preserved in the image. MSE is mean square error. PSNR is basically this is peak signal to noise to ratio, that is very common to measure the quality of any images between two images, basically LP IPS, MSSM IM. So like this we are going to have basically all these numbers generated here, and we found let's say that this PCS GAN basically performs better than existing methods of that time, basically here over that particular data set, which is basically WHU IIP face data set, basically converting image from let's say domain A, which is thermal, to domain B, which is basically going to be the prism. So now I will take only 3-4 more minutes to just give you some sort of let's say clue that what kind of basically applications where people are exploring the GAN models. So now if you see, if you want to generate let's say a lot of cartoon characters, then we can again we can learn a generative adversarial network to generate more and more let's say samples in case of the cartoon characters here. And if you see, this is one of the very recent area where, suppose if you are having a sentence and you want to generate an image with respect to that sentence, that suppose if we say that, let's say this bird is red and brown is in color with a let's say stubby beak. Suppose if this is your input, now it is very surprising that okay, we are able to produce that. We are going to visualize with the input which is in the text form, and we are going to ultimately produce a corresponding output. Even the day is not let's say far when you are going to think something and the same image will be produced by your let's say computer. So let's say brain signals can be captured, and that signals can be basically can be used with this deep learning models even to just produce that what you are thinking in your mind. Even that can be basically that image can be directly generated by the computer, and these things will be true very soon. So now if you see, this is one of the recent, let's say, area, that text to image translation. Basically, if you have a text, then you can use recurrent neural network in order to find out the features from the text, and those features will be used with the upconvolutional neural network of this generative adversarial network, or basically generator, and then it can produce the image. And because you are going to have some ground truth image also as real images, then actually it can learn that okay, if this is the text, then what kind of image it should generate. Similarly, suppose if you want to do a lot of kind of a, let's say, image processing where we want to do let's say image corrections. So suppose if we have let's say faces which is not frontal, but if you want to generate the frontal faces, then this can be also posed as an image to image translation problem, where non-frontal faces are going to be the faces in let's say domain A and the frontal in domain B, and we can learn this let's say generative adversarial network model such that at the test time, if you are going to have any let's say face which is non-frontal, then we can generate actually the frontal faces corresponding to that. Obviously, if this is all these things are going to lead to let's say huge advancement in all these artificial let's say intelligence area, where basically let's say in future let's say all these things, when it is going to come even in the real life scenario, then it is going to basically help a lot of it is going to provide a lot of help let's say in biometric area or in surveillance areas in let's say different applications. This is something just let's say kind of a let's say more kind of interesting work, where basically if you want to generate the face of the people that after that many number of years, how this particular person will look like, then we can basically again use this generative adversarial network to let's say generate the images at different let's say ages. This is also one of the very recent techniques where this generative adversarial network is being used for the deraining. Suppose if you are having a picture and let's say if you want to, and let's say there is an effect of the rain because this picture is taken during the rainy day, they are raining time. And if you want to reduce the effect of the rain from the picture, then again generative adversarial network is being used. So you can also refer some of the recent techniques that people are actually using for such type of things. So even if you see, this is going to have basically very nice applications in real life scenario. Even in let's say in case of driving, it is going to be very much useful. In suppose in case of driving, let's say even there is pictures which is basically having the raindrops, but your systems can show you the clear picture by removing the raindrops. This is another application of photo in painting, where basically suppose if you are having an image and suppose if there is some holes in the image, then again generative adversarial network can transform in such a way that it can fill the hole based on let's say other appearance. And this is again going to be useful in different applications. Suppose let's say suppose you are going to have a lot of very old documents and some parts of the documents are going to missing. Then basically when you are going to basically take the picture of the document, and suppose if something got erased or not available, then basically these inpainting algorithms can be used to basically reconstruct that whatever is not available in the let's say actual image. Super resolution is again going to be basically one of the application using generative adversarial network, where we can have a let's say image at a smaller scale as the input, and we can produce an image at a higher scale as the output, and that can be useful basically at different places where high resolution images has to be created. this is another application of dehazing, where also this generative adversarial network is now being used very heavily. Suppose, let's say, this is very common scenario in the, let's say, states where, let's say, cold is there, that lot of haziness are there, let's say, mostly in the morning time. If you take the picture, then picture will not be clear due to the presence of the haze. Then what can be done here? Basically, again, generative adversarial network can be used basically to transform an hazy image into a clear image, and the network will learn automatically in such a way that it can find out the pattern of the haziness, and basically it can reduce that effect, and it can produce basically the clear picture as compared to the, let's say, hazy pictures. So now if you see this generative adversarial network, though it is started in 2014, but now it has become, even if you see the traditional generative adversarial network, nowadays people will say that that has become obsolete, because plenty of improvements has been done in generative adversarial network. So if you see, you will find, if you just see the research papers that is coming in generative adversarial network, now if you see the top conferences or top journals, nowadays you will find that at least 30 to 40% papers that they are publishing are actually publishing, let's say, on the generative adversarial network. Or there is another area nowadays where a lot of papers are being published that is called neural architecture search. That is also one of the, let's say, area which is basically developed in past 2 years, and plenty of works are happening in that particular area also. But in generative, even that neural architecture search also now being done using generative adversarial network. So now if you see, this is just one kind of a repository that if you just search by using this word, the GAN, you will find one repository on GitHub, and they generally they update the new models in this generative adversarial network that comes every day. Every day, a lot of new models are coming in generative adversarial network. So now, what is happening? If you see in artificial intelligence area, after booming of this deep learning, let's say a lot of people have actually started working in this area, and any area which is actually getting more attention, a lot of people are generally getting started working over that particular problem, and a lot of works are happening. So even if you see any trending area, either it is reinforcement learning, or it is generative adversarial network, or it is neural architecture search, so a lot of people are working in those areas nowadays, and plenty of let's say research papers are coming day by day. So if you are interested even to find out let's say different works that has happened, you can just have a glance over this GAN, basically this repository here. So with this, I am going to end today's session. As a summary, basically what we have discussed here, we have discussed that what is unsupervised and supervised learning models, and autoencoder is one type of unsupervised learning model, but that is a very simple model, because there we can very easily visualize that what is our input and what is our output. And when we are extending that particular concept to generative adversarial network, then actually our input has become a random vector, and basically then in order to train our generative network, we are taking help of another network which is called the discriminated network, basically which tries to take the inputs that is generated from the generated network as well as the original input, and based on that it is going to basically have a minimax kind of a two-player game, and the whole generated network and discriminated network will be optimized. And then basically this generative adversarial network, what is the main application of original generative adversarial network is to generate more and more samples in a given training set. For example, if you talk about the cases, let's say the applications where you have very limited training data, then the generative adversarial network is nowadays being used very heavily to generate more and more samples, which is very similar to your original samples are in the same training distribution, such that more and more samples will be available to you in order to make your training even much better. And another let's say domain where this generative adversarial network is basically used is that is very wide domain of image-to-image translation, where instead of having the random let's say weights or random parameters, you are going to have basically let's say one picture itself or one input itself that is in another one domain, and your generator will not have let's say on the up-convolutional neural network, rather it can have a full-fledged autoencoder or even some sort of a network that can basically just transform one image from one domain to another domain. And then on top of that, we are going to have the discriminator basically that will guide this generator to learn let's say in a better way. And then it is going to have plenty of applications. And if you see here, this is one of the area that started in 2014, and a lot of work has happened so far. And now people are actually going for basically how we can reduce the complexity of this generative adversarial network, such that it can be even used over the resource constrained devices. So now overall, if you see where research is growing basically in computer vision domain, so research is growing in few areas which is going to be very trending in coming decade. One area is, even the deep learning is very successful, but it is successful in laboratory setting or in very real, in very let's say controlled setting. It is still not successful over let's say real life data, because it has limited robustness. So that's why this is one of the application or one of the area where in next decade people are actually working, that how we can increase the robustness of these deep learning models. The second aspect of deep learning models or any convolutional neural network models, its weights are very heavy. It takes too much time basically in order to do the training, and even once the model is trained, even it is taking too much time in order to do the inference, then it is very difficult to utilize such kind of model over resource constrained devices, or basically mobile devices in real life scenario. So this is another application where a lot of work already started working, and next decade is going to be devoted to that, is to basically come up with the lightweight CNN models, basically to perform the kind of a CNN pruning. The third area where let's say next decade is basically going to work is basically the area where even we are suppose you are going to have let's say now if you just you can find let's say more than 10,000 CNN models that has already proposed. Which model is better suitable for which kind of data? This is not known. So then can we design a system where the model itself can be designed from the data? Means if you have a training data, for your training data, which model will be better? The model itself can be designed by the network, and that is called the neural architecture search, and that is actually one of the area which is basically growing very fast. Another area where people are working very fast, that is called deep reinforcement learning, where basically network is trying to learn from its mistake automatically, and it is doing the mistake, and based on the reward policy it is trying to learn that such that in let's say in future it should not do the mistake. So with this, I'm just going to end this session, and I will just have some 5 to 10 minutes because I have my class scheduled. So I just have only 5 minutes left with me. I have class from 11:40. So if you have any questions, I would like to take in this 5 minutes.
So thank you for such an informative and content-rich session, sir. We'll take one question, sir. Can we take one question?
Yes, yeah, please.
Sir, Dr. Harish wants to know about with the existence of deep learning network, don't you think the scope of the feature engineering is lost? Most of the researchers feel they are working with a black box without understanding the inner principle of networks.
It is not lost. It has been already lost. Actually, it was lost 3-4 years back itself.
Okay, sir. And one more question. How GAN is useful in medical engineering?
In medical engineering, this is going to be again very useful, but the only problem in medical engineering, until we are not going to have the explainable artificial intelligence, means even let's say if your network is going to give you some decision, but can we let's say convince that on what basis it is going to give this decision? So that is called basically explainable artificial intelligence. A lot of work is happening in that area. So once that area will grow, then only this deep learning basically can be let's say helpful much in the practical scenario. People are doing a lot of work in that area, but still it is not being accepted by, if you see, the experts or doctors. They can only accept once if something kind of a diagnosis or something, then they will accept. But suppose if you are going to basically give some decision, then doctors are not basically happy until you are not going to give the reason behind that. And that is one of the problem with these deep learning models, that we don't know that what is the exact reason that why it is producing this output. But for that, actually a lot of work is happening, that is called the network visualization. So people are actually doing network visualization to find out that what is the, let's say, what kind of, under what scenario basically what kind of neurons are basically activating, and what is happening inside this network, so that it is giving this particular output. So obviously in coming decade, this is also one of the area that people are working. Obviously it is going to be useful. But another problem in medical domain is there is a limited data. So once people are going to basically have huge amount of data, then again this is going to be more useful.
Thank you, sir. We have only one last question, sir, please. In
Yes,
the text to image generation, what if we have the large number of images which is very similar to one another?
That can be also done. Yeah, that can be also done. Then in that particular case, it will not be a paired scenario. Means if you are having a sentence, then you will not say that for this sentence only this image is the output. Then you can say that for this sentence, this is for this sentence, these are the set of images that can be the output. Then it will try to generate let's say one new image that will be follow very similar let's say trend or very similar appearance.
Thank you very much, sir, for your precious time. Actually, thank you very much, sir.
Thank you very much, Dr. Rupas. So is there any other question from anyone else?
No, sir. No more questions, sir. Thank you.
Okay, so then I would like to thank everyone who attended this session, and I hope that you'd have got something from this session. And even in case if there is any let's say problem, or in case if there is any confusion or something you did not understand, you can directly write email to me, and I will try to respond as soon as possible.
Thank you, sir. Thank you for your guidance. Thank you, sir.
So thank you very much. So with this, actually, I am now leaving because I have my one class scheduled at 11:40.
Sure, sir. Sure.